Alright, here we go with Advent of Code Day 13, back at my home setup, so very happy about that. Come on, load. Load, please. There we go. Okay. Let's get our input. While that's loading, we can read. Okay. Every bus has an ID number, indicates how often leaves, timestamp, number of minutes. Okay. Okay. Gotcha. Okay. What is the idea of the earliest busing? Okay, this is actually some interesting code. Oh, wow. Okay, this is the entirety of our input. In fact, let's not even bother with it. Let's just say let's figure out what these two numbers are. So here the earliest timestamp is 9:39. Timestamp, and then we're gonna say. Actually, we're probably going to want to split that. Okay, fine. We can keep it as a file to list, and then we want timestamp is equal to int of L of 0, and then the IDs is equal to L of 1 dot split on the comma character. Oops, extra parenthesis. Oh, I forgot to actually put the text back. Great, now we've got our things. Okay. First line is estimate the earliest timestamp you could depart on a bus. Great. The second line is the bus IDs that are in service according to the shuttle. X are out of service, so you ignore them. Okay. So in service is equal to ID dot filter lambda x not equal to x print in service. Oh, I keep forgetting to. Oh, and we need to turn that to a list. Oop, I didn't mean to full screen that, sorry. Okay, so now we only have the ones that are in service. That's what we want. Great. The earliest bus you could take. What is the ID of the earliest bus you can take to the airport multiplied by the number of minutes you'll need to wait for the bus? Excellent. So to find that, we have all this information now. So now what we need to do is for ID in, ooh, that looks like I used reserved. Bus in service. Print bus. Okay, that's what we want. We're going to take best bus is equal to, I'm just going to, none. if, or actually we can just say in service of 0 for bus and in service. The number of minutes waiting, okay. Min wait is equal to, we want the remainder when we, so say it's 15, then it'd be 1 for 7, so it's literally the modulo. So it's in or best, nope, we want timestamp modulo best bus. If timestamp modulo bus is less than min wait, or best bus equal to bus, min wait is equal to timestamp modulo bus, and then at the end we want to print best bus times min wait. We forgot to turn these into filter map int lambda x int x. 26. That's not right. Maybe it is right. Nope. Okay, not surprised. Let's see if we get the right answer with a different input. Because this will just be the fastest way to test it. We're into 771. And this is wrong. I think we're off by 1 minute. I think that's the thing happening right now. Because or 2 minutes, there's something's not quite right. Oh, you know what the problem is? We're taking modulo, which is finding the thing underneath it. We want the thing over it. Oh, okay. Okay, so it's not timestamp modulo best bus, it's timestamp modulo best bus plus best bus. Maybe? No, that's not quite right either. Let's think this through for a second. So these numbers are just big, which is annoying to think about. So we arrive at a time, and we want to know what the next time is that a bus arrives. So I think it is timestamp modulo best bus, and then we add I think it actually might just be best bus minus timestamp modulo best bus. Let's think about that for a minute. So in this case, best bus is 7, so it would be 7 minus timestamp modulo best bus. So this modulo 7 is 1, so 7 minus 1 is 6. So the weight would be 1, 2, 3, 4, 5, 6. I actually like that. Let's try this. Best bus minus best bus minus 5. 5 minutes. That's what we want. Okay, let's change this to in1. Oh, sorry, not in1, just in. 410. Oh, no, not 410. There we go. That's the number we want. Not the right answer again? No. That's not what we want. Because we got bus 59. It's 5 minutes before it departs. I guess one thing that, but there's no way that would be the answer. One, two, three. 10-minute wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That looks right. Two, 224, 270. That's why it isn't best bus, it's bus. Stupid. 102. There we go. Man, that was really slow. Okay, part 2. The shuttle company is running a contest. One gold coin for anyone. Time sensors. The first bus ID departs at the time. At that time, and each subsequent listed bus departs at that subsequent minute. First line of the input is no longer relevant. Excellent. Such that bus ID 7 departs at T. Earliest timestamp. I knew we were going to get to the modular arithmetic part of admin of codes soon. Let's see if we can start thinking through this. So now we actually do need the IDs. We need to iterate through those. Let's just call this all IDs or map int IDs is equal to list map lambda x equals x. If then we want x, else we want int of x, and then we're going to give in the IDs, print int IDs. How does the ternary work in Python? Right. X if that, else. That's what we want. Great. So now we've got all those numbers exactly where we want them. So we're looking for something that's a multiple of 19, and where this far out from it, we get something that's a multiple of 523. And then, and this far out from it, we got something that's a multiple of 37. This is modular arithmetic up the wazoo. So let's think about this for a second. So we're saying we want to say that we're trying to find timestamps t such that t is equal to, or t modulo 19 equals 0, and t plus a bunch of things. Let's just call it n modulo d equals 0. So and then that's what all of these systems of equations are going to look like. It also means that in this case we'd have like 19t or there would be some number such that like 19x plus n is equal to 37y or something like that, where I think I'm going about this in entirely the wrong way. I'm going to do some quick Googling of modular arithmetic properties. Let's poke around. not quite sure how to do the math for this. And we've got something like 9 constraints. So iterating just until expecting to get a magical solution would be absolutely insane. Wait a minute. Wait a minute. I think we might be able to use the Chinese Remainder Theorem on this? I'm not certain. Because the Chinese Remainder Theorem is used to solve a bunch of equations where it's x is equal to a mod b. And what we're looking at right now is equations where it's t plus n mod d equals 0, which I think we can move around to say, like we can subtract n from both sides and say t mod d is equal to n, or negative n, right? Like we can just subtract n. Or even if we want to do it a different way, we can add d and then d minus n. T mod d is equal to d minus n, so x is equal to a mod b. We've got this t here that's always the same. Wait, okay, so here's what we got. A mod b, and the modulo is always staying the same, and the d is, sorry, the d is changing, and the n is changing, the t is staying the same. So what we really want is n mod d is equal to, it's minus t. And that's the equation that we're getting everywhere. So I might actually just try plugging this into an like a Chinese Remainder Theorem calculator, because that's what it's looking like to me. So let's try just converting this into like a readable Chinese Remainder Theorem thing. So we want equations that are x equals a mod b. I'm going to do a little bit more poking around with the Chinese Remainder Theorem and find a good... So Chinese Remainder Theorem, let's just look at this right here. We've got x is equal to, or congruent to, a mod n1, ak mod nk. So we want a bunch of different things that are all like this. Excellent. And so now what we need to do is figure all those things out. So all of these are t plus n mod d. So the plus n bit is the index, and the d is the number itself. And then the thing that we're doing to shift it around is we're subtracting t from both sides, and we're ending up with negative t on the right. So now we're ending up with negative t is equal to n mod, congruent to n mod d. So let's print out all those things. So we've got all the int IDs. Now for I in length of int IDs If int IDs of I is not equal to x, then we want to do stuff, and then we want to print a mod n. So let's print I comma int IDs of I. Just comment all that out. And now we've got not iterable. This is in for I and range. Okay, so let's just try plugging these into a Chinese Remainder Theorem calculator, because those exist and I don't feel like figuring this out right now. Number of equations, so we have more than 6, so this isn't going to work. Oh, why are there limits? 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9. Dang it. Okay, let's see how hard it is to implement, because now I just want to Chinese Remainder Theorem. Let's look for one more calculator, because I did see this thing elsewhere, and I feel like this might be easier. Okay, so let's try the remainders. So we've got 0, 19, we've got 13, and if this doesn't work, then we're kind of screwed, because we have to start all over, typing everything in. 37, and then 19, 523. And we've got 37. And if I type something in wrong, that would also be very bad. So we'll probably check this over at least once. 42. 42. Oh, 42. There we go. 23. 48. 29. 50. 547. 60. 41. 60, 67. 17. Calculate. Okay, we got a number. Let's just double check all of our things. So we've got 0. Oh, and this is also the negative number. That's the other thing that we have to remember. So we're gonna have to flip it around somehow. So we've got 0 mod 19, 13 mod 37, 19 mod 523, 37 mod 13, 42 mod 23, 48 mod 29, 50 mod 547, 60 mod 41, and 67 mod 17. Great. So now what we know is this is equal to 0 mod 19. Is equal to 13 mod 37. Let's just try it. If it's wrong, we'll figure it out. Not the right answer. Okay. So I think that I need to flip something around a little bit. One issue is it might not be the smallest solution. That's something to consider, because I don't think this remainder guarantees that. I'm not sure. Another thing to consider is whether or not we're calculating the right thing, because I am... Ah, yes, okay. Yes, so that, okay, I think I might see why it's wrong now. So what I really want... Sorry, I know it's not very interesting to just watch me thinking through this. Let's just think about this for a second. So we've got this. Oops, I did not want to put that in a new... Don't save. This is equal to 60 mod 41. So what we really want is a number such that t plus 60 mod 41 is equal to 0. You know what, I think I'll fix it. I think it'll fix it if I change all of these remainders to be negative. I'm not sure if it'll let me do it. Let's just see if it gets upset when I do that. Nope, that worked. So let's just make all these negative, because I think that'll accomplish the same thing as trying to flip the other thing. And that's a very different number. It's upset with my ad blocker. Oh no. Whatever will I do? And that's it. Wow, and we got 609, even with all of this slowness. Wow. Okay. Wow. Yeah, okay. So I was very, very slow in part 1, but because I knew what the Chinese remainder theorem was, I managed to get part 2, even though it took me 20 minutes to figure it out and get it plugged into this website. So what I'm probably going to do next is figure out how to code it up, because it's kind of a cop-out to use this Chinese remainder theorem solver website. I'll probably just follow this little explanation they have here, but man, yeah, if I'd realized earlier that these equations just work together to make this Chinese remainder like that's what these modulo problems really are, is they frequently turn into, like, you know, the Chinese remainder theorem, or the, what are the other ones that are super classic? Euclidean division, yeah. Modular arithmetic really throws me for a loop. Cool. Well, If you made it this far, great. It can be summarized to know how to do modular arithmetic correctly, and for part one, that's why part one was so unbelievably slow, was because I, used the wrong variable a couple times and thought about the problem slightly wrong. And then for part two, it's just know the Chinese remainder theorem and how to apply it. The reason that the negative thing happened is I was subtracting t to get t over onto this side, but that makes it negative t. So I was like, oh, well, instead I could just multiply by -1, have all the n's be negative, and that gives me, all these lovely negative numbers, and that gives me the actual thing. So for some reason, this is the negative version of this other garbage number. So yeah, good stuff.